All right, so again, Cramer's rule is going to be an application where we're using matrices and their determinants to solve a system of equations, okay? So click to the first page there. I have a generic 2x2 system. It's two linear equations in two variables. All right, and first I'm going to try to solve this just by the algebraic method of substitution. Okay, actually, let's do it. I want to do elimination. So cross that out. We'll say elimination. All right, so there's a couple different ways I could do this. How about I multiply the top equation by c? I'm going to write that below here. I'm going to say that's ACX plus BCY equals CE. And then how about I multiply the second equation by negative A? That's going to give me negative ACX minus ADY equals negative AF. And that would allow me to add the two equations together to cancel out the first set of terms, cancel out the x variable, right? And then that would leave me with BCY minus ADY. Those are not like terms, so I can't currently combine them. Equals CE minus AF. All right, now, I don't have like terms on either side, but on the left side, I do have this y in common. So what I'm going to do is factor it out. And then I could solve for y by dividing that whole set of parentheses over, right? So let's bring that up here. I'll make this y equals CE minus AF all over BC minus AD. And what I'm going to do with this, I'm going to manipulate it by multiplying by a clever form of 1. I'm going to multiply the top and the bottom by negative 1. All right, so that's going to turn CE negative. It's going to turn negative AF positive. So I'm going to reorder this. I'm going to make this positive AF minus CE all over positive AD minus BC. And I'm going to think of this now in terms of if it came from a second order determinant, each of the numerator and the denominator. So if the numerator is AF minus CE, that would have been found off the second order determinant AE in row 1, CF in row 2, yes? AF minus CE. Okay, and then down below, AD minus BC would come from the second order determinant of AB, CD. Right, AD minus BC. All right, so this gives us a formula for y in terms of two second order determinants. All right, so I'm going to list that down below. Y equals AE CF over AB CD. Now, I could go through a similar process and try to come up with a formula for x. And if I do that, I'll end up with the following. The denominator will end up being the same, a, b, c, d, the same second order determinant as y. But the numerator will end up being EFBD. Okay, now notice how you can get from the system when the two equations are written in standard form like they are to both of these setups. Treat them like formulas, okay? So notice for x, the determinant that's in the numerator of this fraction, look at the first column. The first column is EF, which are the constants. The second column is BD, which are the coefficients of y. If you go over and look at the numerator of y, notice the first column is AC, the coefficients of x, and the second column is EF, the constants. So what that tells me is whichever variable I'm solving for, that that column that represents the coefficients of that variable gets replaced with the constants, right? So if I'm solving for y, these are the coefficients of y. They are going to get replaced with the constants in that second column. If I'm solving for x, right, these are the coefficients of x. They're getting replaced in the first column with EF. But notice that, again, the denominators are both the same. A, B, C, D, those are the coefficients from the variables on both equations. Okay. Nice thing about Cramer's rule is it allows you to get fractional solutions without ever having to potentially calculate with a fraction, right? If I make it so all of my coefficients are integers, I'm able to calculate these determinants using solely integers, but I'll still be able to get a fractional answer. Okay, so that's kind of nice. All right, so let's go to example 1. Use Cramer's rule to solve the system. Both equations have to be in standard form, which they are. X and y are on the same side. So let's go after x first. The determinant of the denominator should be the easy one. It's just the coefficients of both variables, right? So the first column is going to be 5, 3. That's the x column. And then the second column, 4 and negative 2. In the numerator, since I'm solving for x, I'm going to replace the x column, those coefficients, with the constants, 28 and 8. But the y coefficients will remain, 4 and negative 2. Okay, now calculate both second order determinants. So 28 times negative 2 is negative 56 minus 8 times 4, 32. I'll clean that up in a moment. Down below, negative 10 minus 12. So that's going to give me negative 88 over negative 22. And this one actually reduces out nicely to a positive 4. All right, now at this point, you could take that 4, you could plug it back in for x in either equation, just substitute it in and solve for y, right? But I want to get more practice with Cramer's rule, so I'm going to set up y as well with this method. Now, I know the denominator should be the same determinant as I got for x, right? That means it's going to be negative 22. The numerator, first column, the determinant will have a 5 and a 3, the coefficients of x. The second column, I'll replace with the constants of the equations, 28 and 8. Calculate this determinant. So that's going to be 40 minus 84 over negative 22. Negative 44 over negative 22 is 2. So, of course, we're going to write our solution as an ordered pair, 4, 2. Questions there? All right, example 2, we got another one. That's a 2 by 2. It's already in standard form. Okay, so let's go after x. Determinant of the denominator using Cramer's rule. First column will be 6, 2. Second column, negative 3, negative 1. Numerator, what's the first column? 18 and 10. Second column, negative 3 and negative 1. Okay, evaluating the determinants, I'll get negative 18 minus negative 30 over negative 6 minus negative 6. These are going to turn to additions, of course. You're going to end up with 12 over 0, which you can't divide by 0, so that fraction is undefined, right? Okay, so this presents a little bit of an issue. What this tells me is we don't have a single solution, one intersection point here. So let's go back up and inspect the original equations. Okay, notice I could reduce the first equation. I could have divided everything by a 3, couldn't I have? So that would have led me to 2x minus y equals 6. And then 2x minus y equals 10. You can't reduce that. All right, well, think, if you put those in the slope-intercept form, they're going to have the same slope, but they'll have different y-intercepts, right? Therefore, you seen this symbol before? That's the therefore, or in conclusion. If I have two lines with the same slope and different y-intercepts, what's that tell me about the lines? They're parallel lines. Parallel lines do not intersect, so what would we answer here? No solution. All right, now let's just pretend, let's say after we reduced, we got here. Let's say both reduced to 2x minus y equals 6 and 2x minus y equals 6. Clearly, they're the same line, right? Two lines, how many points do they share? They share all the points, right? So we're not going to say all real numbers here. All real numbers is a one-dimensional answer. We're talking about two-dimensional ordered pairs here, right? So the better terminology would be infinite solutions. And if we want to be really formal, we can use set notation. We can say our answer is the set of ordered pairs on the line represented by the equation 2x minus y equals 6. Cool. So watch out for, when you get a 0 in the denominator. You're allowed to get 0 in the numerator. 0 divided by anything is still 0, right? It's just the denominator that will lead you to one of these two conclusions. All right, let's do it with a 3 by 3 system now. The setup is the same as it was for a 2 by 2. So we're going to set this up for x, solve for x, and then we'll just set up y and z. We won't take the time to actually solve for both of those. Okay? All three equations are already in standard form, so we're good there. Okay, so if I want x, I'm going to have a third order determinant in the denominator. 2, 1, 1 would be column 1, the coefficients of x. Negative 3, 2, negative 3. Second column, coefficients of y. 1, 1, 2. Third column, coefficients of z. Make sure you copy the numbers down correctly. Sometimes students don't copy the negative sign, right? And that's going to throw everything off. In the numerator, what's the first column? Yes, I'm solving for x, so the coefficients of x need replaced with the constants. Second and third columns, though, should be the coefficients of y and z. All right, so you have two third-order determinants to evaluate here. You can do diagonals or expansion by minors. My strong suggestion would be expansion by minors. Diagonals, I find the work just kind of gets lost all over the paper, okay? So I'm just going to use the first row in expansion by minors. Okay, so 5, its minor would be 2, 1, negative 3, 2, minus negative 3, times its minor, negative 1, 1, 1, 2, and then plus 1 times its minor, negative 1, 2, 1, negative 3. I'll clean that up here in a moment. Let's expand out the bottom. 2 times its minor, 2, 1, negative 3, 2, minus negative 3 times its minor, 1, 1, 1, 2, and then plus 1 times its minor, 1, 2, 1, negative 3. All right, evaluate your second order determinants there. So you'll get a 4 plus a 3, add 3, negative 2 minus 1, add 1, 3 minus 2. Down below, you get a 2 times 4 plus 3 again, plus 3 multiplied by 2 minus 1, plus 1 multiplied by negative 3 minus 2. Okay, that's going to give me a 7, a negative 3, a 1, a 7, a 1, and a negative 5. Now I'll do all my multiplications. 5 times 7, 35. 3 times negative 3 is negative 9. 1 times 1 is positive 1. Down below, 2 times 7, 14. 3 times 1, positive 3. 1 times negative 5, negative 5. Okay, that's going to give me 27 over 12, which reduces to 9/4. Notice how I was able to get a fractional value without ever having to calculate with a fraction. That's kind of nice. Okay, now let's just set up y and z real quick. For y, I know the denominator, I'm just going to say that's the same as x. Numerator, first column will be the coefficients of x. Middle column will be the constants. Third column will be the coefficients of z. For z, denominator should be same as x. First column, coefficients of x. Middle column, coefficients of y. Final column, constants.